I don't know, back in about 2010, 2011, I decided to take an astronomy class because I was ready to buy a telescope, and I got a big telescope, and then I couldn't really see anything from my driveway. And so I started using the digital camera I had, and it worked pretty good until it got warm out, and then the quality was just terrible. So I was lucky enough to get a CCD camera and filters for Christmas. It's the same camera I own now, and it's still running really well, but I just couldn't get anything out of it. I spent several months and just didn't get anything. And then I saw a write-up about atom block and workshops that he held on Mount Lemmon. And I thought, boy, that sounds really neat. So I signed up and went and spent a few days there and came home, and within a week I had my first image. And I actually still process just about all my images the exact same way. That's some of the reason why I like to tell people I spend a good 10 minutes on them. I know there's more there, and I eventually attended another one of his workshops where he was just getting started with PixInsight, but I really haven't moved to it yet. It just, I'm old and kind of set in my ways right now. Maybe at some point, if I ever retire, I'll go back and reprocess all my images and find all the stuff I missed. But because of Atom, I still image, and I think I get pretty good results, and I use the same tools that he taught me many years ago. And so I'm really happy that I reached out to Atom, and he was gracious enough to join us tonight and go over some PixInsight and some of the questions that the group sent to me. So with that, I'll turn it over to Adam.
Well, thank you, Dan. First, let's do a quick sound check. Can everyone hear me clearly?
Yes.
Yes. Yep.
Sound quality is good. So yeah, Dan, I mean, it used to be me that would produce the largest the rate of images, the largest number of images per unit time. I used to hold that record. This was back when I was at Kit Peak, because it was my job. Literally, I had people coming almost every night, and I had to make the images for them. And I would like to do that and not have them wait for a week or something. So that used to be the way that I would operate, and people were always so impressed. You have taken that trophy. You produce more images per unit time than I think anyone. So of a very standard, good quality image. There is an argument to be made, of course, that you could try to do more with the images. One of the nice things about PixInsight is that it is amenable to doing what you would probably might call a pipeline, where you do a certain set of operations almost every time, and then you might do some other little tweaks and then say, oh, that looks great, and move on. So one of the nice things is the scripting part of PixInsight that allows you to do that, or at least kind of automate a lot of that. Now, having said my Dan story, I guess tonight I come to you in a state of quantum preparedness, where you guys are going to be the observers, and you're going to tell me, you're going to collapse my wave function. We'll soon find out whether I'm actually prepared or not. I would say I'm in a bit of 50-50 kind of place. I wanted, obviously, to address the very particular questions that Dan passed on to me. So that's what I'll be doing tonight. And I'm just going to point towards a couple of examples that are like that. So I have 3 or 4 kind of small vignettes of things that I'd like to demonstrate. And if I end early or run into problems, because this is live and I don't have anything prepared like a PowerPoint or anything like that, this is going to be just a live demonstration of some of these things. If I should go through them very quickly and there's still time and you have something else that you would like to see, something that I might be able to do in the time allotted, then I'm happy to do that as well. So for those that don't know me, is there anyone that is unfamiliar with a little bit of my backstory? Does anyone not know who I am by any chance? Does everyone? Because I can keep it really short. So my biography is that I've been working in astronomy for my entire life, basically. I studied astronomy and physics in school. After I graduated from the University of Arizona, I got involved and basically developed what is now the Kitt Peak public observing program, which allows people to go to the mountain at night and observe through a telescope. So those programs still take place, and I was there from '96 until 2005. But I wanted to do bigger and better things. So I eventually approached the University of Arizona, came back basically, and tried to convince them that they really wanted even bigger and better nighttime program. And so that came to be, and I founded the Mount Lemmon Sky Center, which is where Dan visited, at the top of Mount Lemmon, which is just north of Tucson, Arizona, and created another set of public outreach programs that I feel are the very best of their kind. In both of these programs over the past, over those 20 years anyway, always part of that were opportunities to do astrophotography, some form of that where people would come to the mountain and participate in the collection of the data and see it processed, or later it would be in some sense being able to remotely connect to the telescope and then collect the data and be participant in the processing of it. So the astrophotography part of this thing is only one facet of what I do, but it is certainly a very important one. And it's the one I'm going to capitalize on tonight. PixInsight became a relatively big deal, I would say, well, probably 5 or 6 years ago now. And it took a long time for me to reach a point of what I would consider proficiency. So, you know, even at the time that Dan had visited me at Mount Lemmon, on the order of, I'm going to guess, 5 or 6 years ago, though I was kind of fiddling with PixInsight, I was not nearly ready to possibly explain things about it. But I've had more practice now because I've really devoted a lot of energy to understanding the program. So that's really the biography of where I am now. And it's my emphasis. The emphasis comes from, I should probably share my screen here. See, look, I made a beautiful thing for you. It's, you know, you get to look at it for 20 seconds. This is the sunset here in Arizona. Does anyone recognize why I might display that picture? This is really tough.
Looks like the flag, state
Very
flag.
good. Who said that?
Well,
That's very
me.
good. That is supposed to look like the flag of Arizona. Excellent. So I have a website in which I have this now content for the instructional videos for almost all the programs that I've used, but certainly my emphasis today is PixInsight. So if you are interested in the kind of information that I'll be presenting tonight, I would encourage you to visit atomblockstudios.com and see all of the stuff that's here. I have many, many hundreds of hours of content on especially PixInsight, but also Photoshop and CCD Stack and things like that. So that's my small advertisement. How about the other thing that I should advertise? Did some of you see the most recent image that I just published? Because I'll be using that as an example tonight. So I am going to suspect that many of you have not seen this galaxy before. Is that true? Have any of you seen a nice image of NGC 3981 before? I think it's a cool one because you generally don't see these, what looks like wind-blown spiral arms of a galaxy. It looks, someone actually said it looks something like the Star Trek, you know, spacecraft in a way. I guess I can see that, something. But
I just saw
thought
this
was
picture.
cool.
I just saw this picture just the other day.
Yeah, yeah. Well, obviously I try to get it out there once I make a new picture. One of the interesting things about the picture though, do you see this terrible, terrible thing going on with these stars? It's really horrible. So this was taken with a large telescope, but the telescope was an as-alt system, which means it had a derotator at the back that rotates the camera to make sure that the object stays nice in the field as you take a long exposure, but the diffraction spikes rotate. And so that's fine for science. Not good if you want to take a pretty picture. It was terribly hard. That was one of many challenges with this image. There's another challenge that I'm going to highlight, not that one. Well, actually, I may show that one too. Both that challenge and another one with this data set that I'd like to highlight because it deals with some of the questions that were answered. So I wanted to show you the image here just as an example. But the first place I'd like to start is none of those things. It's actually an update. And the update is something that I think is relevant because it highlights a number of tools and techniques in PixInsight. So I'm going to show you an update to a technique that I developed that helps to de-emphasize stars. And it will highlight some of the things that have been asked. And then I'll move on to very specific elements of this. Let me bring up a picture and explain why you might want to do this. Now I haven't navigated to, I put all this stuff in a directory, but now I need to go find it. It should be here. There we go. And then here, and I will open up, now I'll just open up one for now. Okay. So here's an image of a nebula that is a fairly star-crowded field. And what that means is one of the techniques that people like to do is to minimize the distraction of the stars, not to make them disappear. That's an entirely different thing. In fact, it's harder to do what I'm about to show rather than, you know, just eradicate the stars is, it's easy. There are several ways of doing that. In fact, we're going to take advantage of one of those ways. But at the end of the day, I want to render the image in such a way that the multitude of maybe many of the medium bright stars to some of the smaller ones, just to dial them back by either shrinking them or de-emphasizing them in some way. And that helps make it possible to really enjoy the nebula a little bit better. So this picture is not very far along in terms of processing. This image is basically just the LRGB version of this particular data set. So it hasn't really been adjusted in terms of contrast and other fancy things at this point. And to get this technique to work, then let me show you back to my website here for just a moment. I have the instructions for what I'm about to demonstrate both online under free videos, although it's not a video. This is, I hate doing this, but I did do this. I made the screenshot explanation of what to do what I'm about to demonstrate. It's all here outlined in gory detail.
Wow.
However, I also have a YouTube website, or YouTube site, I guess, and channel, that's the word. And you can see the, let's see if I take a step back here. Yeah, you can see the videos that I have available. Many of them are on PixInsight, though some of them will be table tennis. So don't be surprised if you see me whacking a little white ball or something like that. It's my other pastime is table tennis. So that's where you'll find the instructions. And one of the cool things I should mention is that, I'm going to go back, in this video right at the end here, I have a nice screen which gives the, there it is, gives the steps. So you can see there are only 7 steps, and I'm going to follow them right now. What I want to do is make a couple of copies of this color image. And the technique that I'm going to employ is different than what is usually used. Usually when you try to de-emphasize or shrink the stars, what you do is you use an erosion filter, which takes the neighboring pixels surrounding stars and kind of squeezes them into the star, making them smaller. But that introduces certain kind of very telltale artifacts. It's easy to tell that you've done it. And some of those artifacts are, they're not very pretty. If you look at an image maybe at a larger scale to really kind of see what's going on in the image. Any image looks great when it's only this big, but you know, sometimes you want to look into the image and see the detail and other elements of it. So the technique I'd like to show does away with that. Now it may have its own artifacts, but it doesn't have this issue of that neighboring pixel value, because I'm going to show you a method that substitutes pixels instead of using an erosion filter. That's the key to this thing. Even if you don't like the technique I'm going to show, or the overall star de-emphasis idea, the tools that I use, the techniques that I use to do the thing are in and of themselves powerful. So the first step is to make a couple of copies, and then I'm going to make an image that will be my substitute pixels. That's what I'm going to do first. So let's do that. So I'm going to make a couple of copies here like this, and then I'm going to make another copy, but see, I've already got it because I don't want to wait around for it, like this. So that's going to be a copy here in a moment, but I'll minimize it so you don't see it. So the first thing I want to do is to generate an image that does not have any stars. Those are going to be my substitute pixels, and that's kind of the key. There are a couple of ways of creating an image without stars. One way is to use a tool that's called StarNet++, and this is available. You can now install this into PixInsight. So you'll see here that I have it as a module that you can run in PixInsight. So there are instructions about how to do this. It's very simple. You just put it in the right directory and then tell PixInsight, hey, there's a module there, and it'll load it in here for you, and then you can use it. But it takes a couple of minutes to do the job. So I made a copy of this image, and then I would drag the triangle here to make a starless version. That is what this thing here is. This is the result of running StarNet++. And instead of calling it a starless image, I'm going to call it substitute pixels. I'll even spell it out. So these are my substitute pixels here. This thing is going to be a version of this image that we can create a mask from. So there are a number of ways of doing this. Anytime you have an image and you want to do something to it, like extract luminance information to create a mask, generally you're going to want to run, and I could do this, well, I can do it anywhere. You want to run a process called Rgb Working Space. Let me demonstrate here. All this does is it makes sure that when you extract the color information or luminance information, that the colors are getting equal weights. That's all this does. So you won't see a change to the image at all, but it means that when I do the following thing, when I extract a luminance, a grayscale version, I'm not biasing this information by any one particular color. That's all that does. So I'm going to be showing you this as if you have some familiarity with PixInsight. If I were just to explain, where I am pressing and so on, that becomes a much longer presentation. I'd like to show the technique rather than just how to use the software in particular. But the button I just pressed allows me to extract only the luminance information. So that's just a grayscale version of this copy of the image here. One of the questions that was asked is, how do you create star masks? And so what I'm about to demonstrate is a method of creating a star mask in what I think is the easiest and fastest way to do it. There is a process here called multiscale linear transform, and there's a related one called multiscale median transform. And I will highlight maybe the difference between them in just a moment, but it's MLT that I'd like to look at here to begin with. What I'm going to do in this image is ask this algorithm to only return back to me scale sizes that are of these dimensions here. That is, structures in this image, things in this image that are these sizes. So the way that this algorithm works is it works on what are called wavelets. And wavelets are a domain. They are a mathematical construct which analyzes an image in both the size of the things that it finds as well as the frequency at which it finds them. So there is something called a fast Fourier transform. That's a kind of signal processing which only looks at the frequency of things. And then obviously you can look at the spatial sizes of things. So a wavelet kind of combines both elements of that. And you can use that as a tool to analyze an image and return some fraction of the information. You can decompose an image into these spatial frequencies. That's what I'm about to generate here. And by taking advantage of these layers to do it, I can capture just the stars. I won't be capturing any of the dark nebulosity. Anything that's larger than a star is going to be ignored, assuming that I choose my layers properly. So what does that mean? Well, it means that I'm going to ignore everything bigger than these layers. So this is a 1 pixel size. This is kind of the 2 pixel dimension, or 4 pixels because it's dyadic. And then slightly larger and larger groupings of pixel kind of scales. But everything above this is going to be ignored. So that's the easiest way to make a star mask, is like that. Now there's other tools which make star masks that do a further analysis of the structures that you find, and it tries to manage that based on the noise level and thresholds and other kinds of things. But MLT is a great way to make a star mask. As long as you pick the appropriate layers, you very quickly get something that can be made into a star mask in any number of ways. This mask then, what we're trying to do is to get stars in this original image here that are only the medium, bright, and small ones, not the very largest ones. You'll see here that a very large star in this creation that I've made doesn't show up very well. It's very dark. And something in this resulting image that is dark means that it is not actually fully part of these scales. The darker something is, in fact, black means it has no relevance to those scales. So that's good. I can take advantage of the fact that it's dark by picking an appropriate threshold and a value that will ignore everything darker than something and everything brighter than something else. So the question becomes, well, what value is this? If I click on the screen, it tells me the value, the brightness value of this thing is 0.12. But the brightness value of one of these little stars is 0.3. One of these little stars, let's see, what's this one? This one's 0.15. And this one, again, is 0.13. So I know that if I, what's called binarize this image, if I say everything that is darker than 0.15 we will ignore, we will get everything else, which is going to not include these big stars. Those are not the things we can either shrink or de-emphasize. They're just big bloated things. They're not something we're going to be able to, they don't really help the overall appearance. In fact, it's nice to have some big bright stars in there. So the process that I need is binarize. Here it is. You can actually click here if you want to just get a number. So you can click around and get the number that you want, or you can type the number in here. I can't remember what number I picked when I originally did this, so I'll pick something. Do you notice how, I'll undo that, notice how the big star disappeared and all we're left with is a bunch of other things. Those other things are, those are the ones that we want to, I think you would agree that that's a fairly crowded set of stuff. If we can de-emphasize that crowded set of stuff, we're going to be making the nebulosity much more apparent. I will call this, because I'm going to be thinking ahead, this is going to be a halos mask. In a moment, to make the stars smaller, we're going to create halos around the edges of the stars and try to substitute these pixel values into here. So let's look at the directions. It said copy and clone, make a subpixels. That's what I did, the substitute pixels out of the starless image. On the original color image, run Rgb Working Space, which I did, extract the luminance, which we did. And then I'm going to call one of those things a loom image, which I will do in a moment, and the other one halos, which is what I just did. I just did this part, which is to exclude all the layers to make the star mask. Now I need to apply a healthy dilation and small convolution to the halos mask. So let me show you that step now. So we have the mask. What I need to do is make these things larger, because I want to interact with things that are just outside of where these stars are, not this region of the star, but the stuff that's just outside of that. So there's a process here called Morphological Transformation, and it'll allow you to grow or dilate these things. What you do is you choose the operator, which is dilation, and then you choose the structure element or the kernel size that's going to go through the image and do the job. So that size is the size that things are going to be grown. I'm going to pick a very healthy number like 7. And then, ooh, they changed their buttons here. I am actually using a version of this program that has not yet been released. I am beta testing it. There's a group of people that get to see so if something crashes, it's not my fault that, you know, it decided not to work. But apparently they changed some of the little buttons here. Okay, I'm going to run this and it should make it bigger. Yay. Then we can put a little bit of a blurry edge there with convolution, like this. So now I have the beginnings of things. If you recall, remember, I still have this clone here. I'm going to make another grayscale version here, but this one I'm going to call Loom. It is the luminance of this color image, right? I don't think I need this copy anymore, but I'm going to keep it in case I screw something up. Let's look at my instructions because I don't want to get ahead of myself. I believe I'm doing it correctly. So I applied the healthy dilation. I'm going to use pixel math and subtract that luminance image from the halos, the halo image, to create halos. That is the next powerful thing. So powerful thing number 1 that I demonstrated was that you can make a star mask really easily with MLT. Powerful thing number 2 is this thing that I'm about to do. I'm going to get out pixel math, which is one of the things I'd like to cover tonight as well, in addition to what I'm doing. And I'm going to put an expression here, which is to take halos minus loom. So these are the names of these 2 images. And what happens is, let's say I have something very, very bright right here. And let's say that this bit is not represented in the image here. So if I have something some value, white, and I subtract it from this image where it's already 0, I get a negative number. Well, nothing happens. If I have a negative number in that spot, it just remains 0. PixInsight doesn't recognize negative numbers in that sense. So it's not represented on the screen anyway. So nothing's going to happen. That's good. But wherever there is a star in this image, which we know there are in all of these places, those star places are going to be subtracted from these white blobs, and that's going to leave little dark holes in all of the stars, thereby giving us little donuts, little halos. So that's the trick. I'm going to go ahead and try. Let's see if I messed something up. No, I didn't. Look at that. Do you see now how I have a bunch of little halos everywhere? But these are not normal halos. This is powerful trick number 2. Subtract a luminance from a star mask to make halos that are exactly matching both the noise and the brightness profile of the original stars. See, these little holes that you have here, they match the original stars to the pixel level. And that's a really powerful tool to be able to use, especially in the way that I'm going to be doing it now. So that's something to remember. There's another element of this. If you thought that the little halos were not bright enough, you can always make them brighter. That's just going to make the effect of what we're about to do even more easy to see, less subtle. So if I wanted to make them brighter, I would just use histogram transformation here, make them a little brighter like that. That just means that they're going to be more significant in their effect when we apply it as a mask. So here is the original image. This is the color image. We now have a mask that we can use, and we have our other thing, which are the substitute pixels. So let me spend a moment and just say something about this image. StarNet++ created an image where it removed stars, but it put in its place pixels. It used some smart thing to put where there used to be stars, like right here, you can actually see it's a little bit pixelated. It put values there. And those values are based on the algorithm, the fancy algorithm that are used. I would just like to point out that if you look at my instructions, I made this technique before StarNet++ was available. The other way to do it is kind of a standard way in PixInsight, where you use You create that star mask what I showed, and then you put it over the image, and you use MMT, let's see that, use this other version, which I'll explain in a moment, to get rid of the stars. And they make these smooth little patches. And then you can blur them a little bit, but then what you do is you add a little bit of noise to them. Here's the patch here. And then when you add noise, you can make it blend in, thereby making a perfect area of substitute pixels. So this is a much more manual way of doing it, and it does allow you a lot more flexibility. You can get a number of different answers in that method, but it takes more steps. With StarNet++, which is what I just demonstrated, you get one answer, but if the answer is good, you don't need to do all the extra steps. That's why I consider what I'm showing you right now an update. Just by using StarNet++ for the starless image, it saves a lot of steps. But I would encourage you, check out the original method as well. It's another powerful thing to be able to appreciate. So now the final thing to do is to put substitute, I really shouldn't have made such a long thing, pixels. I need to apply my, where's my, oh, here it is. I need to apply this as a mask here. Let's zoom in. You should see that we have stars and the halo is surrounding the star. And of course, I know that because we expanded the mask so it's bigger than the original stars. So that's a good sign. And then let's look here at a region where, there are lots of, I don't know where. Oh, that looks like a nice place. Let's zoom into here. There are lots of little stars and things here, right? So what we're going to do is put our substitute pixels, these pixels here, into those halos surrounding the stars. Now this is subtle. Ready? Boop. Did you see the difference between this and that? Now someone needs to say something out there. Could you see the difference? Is it coming across on Zoom?
Yes. Yeah, it looks good. Nice.
There you go.
Sharp.
Now, this is a different result than what you would get with an erosion filter because I'm not using neighboring pixel values. I'm getting the pixels from this image to substitute into here instead of trying to drag the pixels that are surrounding these stars inward, which has a blurry, weird artifact that starts to look terrible, actually. So that's one iteration. And then, of course, people would say, well, Adam, I want to do it again. I want smaller stars. I want less of it. Well, I'll get to that in a moment. Let me just show you in the zoomed out sense. I know this will be hard on Zoom to see, but here it is before and after. Can you see how the many medium bright to small stars become de-emphasized? That's the idea. Not disappear, but gently de-emphasized. So if you want to do this trick again, you can. What you do, let's see, where was I? I don't know where I was. What you do is I'm going to take a couple of steps back here in my halo mask. Last time I enlarged these stars by 7 pixels, dilated by 7. This time I don't want to dilate by the same amount because in this image now, the stars are a little bit smaller. So my mask needs to be also a little bit smaller, and then I can do iteratively the same thing again. So this time I'm just going to take Morphological Transformation, which is still out here somewhere. Here it is. And this time I'll just enlarge by 5 instead of 7, like that. And then we do a little deconvolution. We won't do 2, I don't know, 1.3 or something, like that. And then we grab a new loom, because this loom is the old loom. The new loom we grabbed from this image that we just worked on, like this. And then we do our trick over here, where we say halos minus loom. So now I have a new set. What did I do wrong? Oh, I haven't called it loom because I just made it. There we go. Live. There you go. So now you have halos again. We apply the halos to the, well, actually it is being applied, but I'll make sure. You apply the halos over here like that. And then we just say substitute pixels, and we write those pixels in. Substitute pixels like this. We write them in again, and I shrink everything down yet again. So now here is one step back. Here's two steps back. So that's the original. Here's one iteration. Here is two iterations. But there is an issue here, and let me zoom in and show you. When you keep shrinking it in, other stars become defined as large stars. A star like this, for example, in that last iteration really shows the effect of where your halo mask was. So there's one more thing I'd like to demonstrate, which is just an excellent use of pixel math and masks and everything else. What we really want to do is, again, just to be sure we're only operating on the small to medium bright stars and not the very largest ones. So, for another iteration, we don't need to do this star here or anyone really like it, right? So what we can do is, I'm going to take a step, well, let's take a step, let's be sure. Take a step back here. And then here, I'm going to take a step back to where we were. Let's see, this is the, yeah, so here's the 5 iterations, right? Well, actually, I'll start from here. I'll just start from here. So this is the original star mask. What you can do is you can use a, I'm going to make a copy of it here. You can use a cool little trick in morphological transformation called closing. The way closing works is that anytime it comes across a thing of a particular size, it closes it down. And if it is less than the structure element that I choose here, so let's say I chose something like 15. If the size of the thing that I chose is less than 15, it'll completely disappear because it gets closed all the way down to black. It just disappears. But if it's any little part of it is greater than 15 pixels in size, then whatever those, if there's 1 pixel left, that 1 pixel gets blown back up into a structure element of 15. So what this is going to do, and I'll demonstrate here, is this is going to make, that's dilation, closing. This is going to make everything disappear except for the very largest things. There. And in fact, with a scale size here, structure element of 15, it's too big. I made everything disappear. So obviously I need something smaller than that. I only want the very brightest stars. Let's try 11. See what happens with that. Right? So if I still wanted, maybe more, I could do 9. There. So these are mostly the locations of the fairly larger stars. I'll still dilate this a little bit. So we'll just dilate this. So this is the, I'm going to call this big stars. This is the location of my big stars. And what I want to do is I want to make the big stars disappear from the original mask. So I just take pixel math here and I subtract halos minus big stars like this. Oh, did I do it wrong? No, apparently I did it right. Let me zoom out and see where some big stars are. So here was, yeah, before and after. You see the very largest stars here, they disappear like that. Now I have a mask which basically just has the very smallest stars. So now I can go back to my 5 here. I would have done this in advance, but I needed to show you the problem before I showed you the solution. Then we have our little convolution. We take halos minus loom. So this should give us our little tiny halos. It does. We make sure that this is being applied here. I do substitute pixels like that. You come here like this. And this time when I shrink the stars the second time, this star right here remains unchanged. It's not being affected because I removed it from the mask. So that is the full technique of being able to de-emphasize stars. Now, it may seem long and drawn out because I explained it, but in those 6 or 7 steps, it would, it takes me 5 minutes maybe to just create the little mask, create the substitute pixel picture, manipulate the mask if necessary, and then de-emphasize the stars. So I'm going to pause here and just see if there are any questions about any of the things that I showed, because this touches on a number of the topics that were passed on to me from Dan. Dan, you're the host, you're the moderator, you're the man. Tell me.
Oh.
Hey, Adam, I had a
Yeah.
question. If 2 bright stars are very close together, does that create any artifacts left over?
Not so much. Where's the mask? Here it is. Something like this,
Yeah.
it's going to eat away at the outside.
Mhm.
It won't really be an artifact per se. And it's especially nice because you're still protecting the cores of the stars. So you can eat away the outside and the core still remains. The problem with an erosion filter is you generally, it starts to like link the 2 things because you're looking at neighboring pixels of the 2 stars, and
Right.
everything that's close to one another tends to start to merge into, that's another downside of an erosion type filter. So not so much.
Okay, good.
Yeah, not so much. Let's see if I can, well, the best way to do it is the following. I just make this line up here. So now I'm going to show these 2 stars. If I blink, no, I didn't do it right. Okay, hold on. What did I do wrong? These, let's just make sure I'm displaying these. So that's like this. That's like this. That could be the problem. Yes. So now I have to find another pair. Oh, look, there's a triple. That looks like fun. It's a triple. So the triple has no real ill effect. Let's back up. Yeah, no, the triple is fine. There's no linking of things. So
That's very nice.
It's good.
Thank you.
Yeah, it's good. Okay. Any other questions about this?
Yeah, Adam, do you prefer MLT to the star mask process, or is there
I
any?
do. It's so much easier. Why go through all that trouble? It really depends on how precise you want the star mask is the answer. If you're looking for precision, literally in the stars in particular within the image. Here, I'm really just saying all of the stars that are, approximately this size. If I don't get them all, it's okay. As long as I get, some very large fraction of them, it's good enough. But for precision's sake, star mask as the algorithm is very nice because it gives you some other tools that I was basically doing here manually. When I grow the star, it's like a growth thing in star mask. When I use dilate here, or when I do the convolution, that's like the blurring that you have, the smoothing that's in star mask. So for most of the things that I do, I just use MLT.
Yeah.
Let me go ahead and just mention something about MLT here. And then there's this other one, which is MMT, which is here. So why would you use one over the other? And the basic thing that I would say as a takeaway is that MLT as a linear transform does not couple one layer to the next in term between the layers. There's no coupling between the layers in the way in which it algorithmically determines what is in one layer and what is in the other. You can directly recompose the image based on those layers as independent things and get the full image back. Now, multi-scale median transform is less precise in that sense. There is a strong coupling between one layer and another. And that is actually good if you want to interact with real astronomical structures, if you're trying to process the image in terms of noise or contrast adjustments or something like that of real features in an image, not for creating a mask, then MMT is the place to be, because you'll find that it gives you better, what I'll call transitions for lack of a better word, a better relevance in the effect that you're trying to do on stars or nebulosity or whatever it might be. So you'll see me whenever I make an adjustment to a nebula, it's going to be with MMT. If I want to capture an element of an image as a mask or something like that, then I'm using MLT to do it. That's the takeaway that I would say as far as the difference between the two.
Okay.
Okay. So I have then, since I mentioned it, why don't I demonstrate something about this difference? I have an example where, yeah, I have, let me clear all of this stuff. I think I can do that. Close on color, that's fine. Yes. Yay. Okay. I have an example image where I use MMT, I hope to my benefit. So let's bring up that image. I said MLT and I really should have said MMT. That's okay. All right. I have this image here. So this image is a work in progress. And since I don't have the full project here, excuse me while I show you the actual image, the end result, which is here and then all the way down somewhere here. So beautiful nebula. Yeah. I'm pretty sure I have a larger version. Yeah, this is a large version. Yeah. So beautiful nebula, it has wonderful details, but one of the things that I do when I look at an image, especially in its more raw form, is I'm looking for elements that I find interesting, that I think are part of the story of the image. It could be the number of stars. It could be the dark part of the sky or the nebulosity. In this case, that element certainly exists here. But there's another thing that I find really attractive. This is a red nebula, but it has these highlights of blue, this kind of filamentary blue stuff within the nebulosity. And I wanted, among if nothing else, at the end of the day, when I'm done, getting to the point of what I call a final image, I wanted that to be represented in the final image. So my way of looking at images is very similar to what I would say, I take this from like Ansel Adams. So I really have in my mind's eye where I want the image to be, even though I don't see that in front of me yet. I can see those elements in its raw form, and then I pay attention to those elements as I process the image so that I protect them or enhance them at every step of the way, and they survive till the end. One of them is this blue bit, and the blue bit is a kind of a cool trick. If you look here, this is just basically, again, an LRGB version of the image. You can tell they're blue, but it's not really exciting. If you brighten up the image more than this, the blue shows up, but it doesn't have the saturation. And if I just straight up raise the saturation, yes, these blues will start to show up, but this red will also very much overpower the blue. Basically, the ratio of red to blue in this image, the red is very, very high compared to the blue. So a straight up saturation is not going to do the trick. Instead, what I want to do is get ahead of the game and try and find a way to enhance the blue information in the image. Now, I believe, let me just see something. Do I have a screen stretch here? Yeah, here it is. Okay, good. So if I hit this button, right, that I wanted to be sure this is actually a stretched image. It's the nonlinear version of this image. We can, I can brighten it a lot. And you can see there's those structures are in there, right? There's blue in there. It just doesn't show up very well yet. It'll be easier to show all of that if I do some trick. So one of the tricks you can do, again, I'm going to run the Rgb Working Space. Where is that? There it is. Here. Because what I'm going to do is extract the 3 color panes. So I now have the red, the green, and the blue, which comprise this image. And one of the things you can do, this is a sneaky trick, but I love doing it, is to increase the contrast of one of the channels. And by doing so, you will effectively enhance it in the final combined color image, in the RGB image. One of the things, though, that will be important here is that if I increase the contrast here of this blue image in some way, which I'm about to show, it'll be using MMT. If I do that, these stars are very, very blue. You can see that already, that they're very, very blue in the original color image. So I might not want to as quickly increase the contrast of the stars. Maybe I should protect those things while at the same time increasing the contrast of everything else. So that's what I'll do here. And now you know kind of the trick to do it. You know that if I want to capture stars in this image in the blue channel here, I can use MLT to do it. But I'm going to need more layers because these things, these are really, really big. So how many layers do I need? I have no idea. I'm going to say we can turn off something that's 1,000, right? Question becomes, how small shall we go? I'm going to make a guess here, but the 64 might actually be the answer. So let's do this. It's close. I mean, I can see here that we're capturing, these guys. And if I use binarize, it'll probably be fine. I don't know if I can go one more step or not. Let me zoom out. See, I don't see any nebulosity at all in the image. And none of these bits of nebula are showing up. So that means I could maybe go one more scale size and just capture that much more. Yeah, see, now you can just barely see a little bit of the nebula. That's the brightest part of the nebula is on that ridge there. Now I've got just about everything that is not a nebula is being captured in what I'm going to call a star mask here. So I should be able to look at that little piece of nebulosity, find out the value. The value is, let's call it 0.1. So I should be able to use binarize and go everything bigger than 0.1. I probably still have binarize open, don't I? Doesn't matter. I'll just go get it again. I don't know where it is. All right, binarize B. Here it is. So if I do 0.1, there, I'm going to be really safe. No, 0.1 is fine. Yeah, I probably should have done more, but it's okay. So now I have everything that's pretty much like stars. Now I'm going to be increasing the contrast of this image, but I don't want to entirely protect the stars. The more nuanced way to do this is I want the stars in the mask to be not black, or not white, or black. Not black, because I'm going to reverse it. I'm going to make them this. So protected. I don't want them to be black. What I want them to be is gray. I want the contrast effect that I'm going to do to the nebula to occur much more quickly than on the stars. And the easiest way to do that and keep everything kind of blended nicely is just to use convolution. So we can do convolution here with, that probably had it out, with some healthy bit of convolution. I don't know how much, but let's see. 10, let's see what 10 does. Ooh, look at that. And if we still wanted even less protection, we could even get out curves. I'm just showing you different ways of doing things here. If you want to make a pedestal, instead of outputting here, do you see how I'm raising this? This is basically going to be the floor of the image. So if I wanted things not to be black, but to be more gray, I just raise the floor, and that should make things more grayish in their color. Just a cool trick if you didn't know that. So let's say that that's my mask. what I'll do is apply it here. So now you can see I'm basically protecting a lot of stars, but the nebula is very free to be worked on in this image. I could, you know, make it a bigger mask, dilate it more. It doesn't matter. So we will do show mask. And then we get out our other cool tool, which is this one. No, it's here. Sorry, it's here. This is the multi-median, so not MLT. Now we're operating on an image, on things that are in an image. So I need to determine a scale size. So obviously I want fairly large scales because the nebula is fairly large. You know, these, someone should have told me, maybe, that I am not on the blue. Oh, yeah, someone should tell me a lot of things here. First of all, there's my mask. See, I made my blue image the mask. I should have made a copy of the image. Okay, there's the blue image. That's the image I want to operate on. I don't need the mask here. Oh, this is on the red. We're only operating on the blue. There. I'll even call this thing a star mask, just for the heck of it. Okay, this needs to go on the blue image. Ah, thank you. Now we're good. So the scale size, how big is this thing? Well, this feature right here that looks kind of filamentary in this thing's about the width of a star. These things here are even larger than stars. So what that tells me is that if I want to enhance those features in terms of a contrast, I'm operating on these scales right here, 16, 32, 64, 128, something along those lines. Now I'm just going to take a shot in the dark. I will show you that, let me just show you one effect. When you increase the bias, you're going to be increasing the contrast. Sometimes people call this a sharpening. I call this more of a contrast. I mean, sharpening is a kind of contrast adjustment, but this is different than deconvolution. So I would call this more of a contrast-like effect. So let me show you what 0.1 does for a bias. It's fairly strong. So it just gives you a sense of the scale at which you're going to be operating here. So here's the before. Actually, it's not that bad. Here's before and after. So 0.1's not bad. It's probably use 0.1 there. Let me do 0.3. Really show you craziness here. Let's see. There. That's 0.3. I think you would agree that that is really crazy, right? We're trying to enhance. We're not trying to beat with some crazy mallet. So I like the 0.1 there. Let's put 0.1 there. And that seems to be about the right scale size that gives me a lot of the filamentary things. But there are things that are a little bit larger than the filamentary stuff that are blue. So maybe I put over here 0.08. And maybe this one I put 0.02. And maybe this one we put 0.05. So I'm kind of centered on this scale size here, but I put a little bit to either side. And maybe that will be my enhancement that I do here. So now I've enhanced the blue channel, and I can reconstruct using what's called channel combination. I can reconstruct the images. So there's the red, here's the green, here's the blue. And what I can do is do this. So this is going to be the new version. And this version here is the old version, the original version. Right? Okay. So I'm going to blink the two. I mean, let's zoom in. I think it's going to be hard to tell. Because this is probably the amount that I would normally do. Probably should have done more. Can you see the blue enhancement there, or is that too hard?
No.
Can you see a little bit of blue is showing up? In fact, let me do one more thing. I want to be perfectly fair here. I'm going to get out, where's curves again? I'll do curves, reset, saturation here. I'm going to do the same amount of saturation to both images. There and here. And now let's do the blink. Do you see how that doesn't have as much blue as this does? Let me zoom out a little bit. Is there another area of blue that's a little better? No, not really. I'm doing the best part. There. So here we go, before and after. You can definitely see it around the star. If you look right around the star here, the blue before and the blue after. So I am just bringing up the blues in the image, and that was one of several steps that allowed me to finally get a version of the image that looks like this, that really does show that contrast in blue. That wasn't the only step, but it was one of several, because you have to do this incrementally to get to a point where you can show off these blue structures, and you can see the other elements of the image that are important to display. So with that, let me pause again. That's another technique, and I think it highlights the difference between using MLT to maybe make a mask and MMT to operate on an image in some interesting way. Are there any questions about that kind of thing?
You find that that adds any noise in the blue channel with that process?
Not at that scale,
Okay.
because I'm really operating on a very large scale. So the, like pixel noise and things like that, you wouldn't see that as an issue. There may be artifacts that are due to the fact that you are at that scale size. There might be a darkness around the things that you're increasing the scale, the contrast of, and things like that, but not at a pixel sense. It isn't like, it's not like a high pass filter effect. It's a different kind of effect.
Adam, I have a question. A lot of times I'll form the RGB from the mono elements, and the colors are surprising, often not very contrasty, and just getting color balance in a way. Are there techniques that kind of get you closer to that from the very start, whether it's a
from the
exposure process or?
Yeah, so from the very start, whenever you have an RGB set of data, typically the issue becomes that the sky itself may dominate, because the object, be it a nebula or a galaxy or something like that, is about the same brightness as the sky. So if you're imaging in a site where it's not very dark, or the sky itself might have, maybe the moon is in the sky, whatever it is, the sky might have a color to it. And that just happens naturally. And it even happens just due to the sensitivity of the chip being different in different wavelengths. You need to take care of that color calibration part of the procedure, which is a combination of both, I use photometric color calibration, PCC, and then on top of it, the removal of any gradients of the sky, because again, it's the sky that dominates. So any gradients of the sky are also going to affect the color. So DBE, or some way to remove gradients, is also important. And then at that point, what you can do is increase the contrast and see what's there just roughly, and go from that point of processing. If there isn't a striking amount of color there, after doing all of that stuff, if there's not enough that raising the color saturation doesn't bring in that vibrance that you're looking for, it may be a hint. I mean, there are certainly cases where you need more information. Many people these days that are using CMOS cameras are taking very short exposures. They take, whatever it is in terms of their time, but they may still not get to the point of getting enough signal to show the difference in the colors, because it's still in the noise. you know, you can see that there's red and green and blue, but the variation in each of those channels are almost equal to one another. So it ends up washing out the color that's in that signal. It's only until you get basically a good enough signal to noise that you're going to be able to distinguish the different colors. And there's one other thing that I would mention just as an aside. Someone recently had a conversation with me, so I'll show you the image. This is about, let's see, www.kyleobservatory.com/gallery/m101.html. Someone was taking a picture of this galaxy, M101, and their complaint was they were using I don't know the size. I'm going to guess it was a 4-inch or 6-inch telescope. I don't think it was that big, actually. And they wanted to get what are shown here are these H2 regions. They wanted to see the pink little bits in the galaxy, and they wanted to see the dust lanes. And the problem is that in many cases, resolution is also important to color. So you didn't tell me which object you were talking about, but sometimes if the color detail is small enough, it all gets averaged out because you literally need to spread the light out more with a larger telescope effectively, or a longer focal length, so that it's easier to distinguish between the changes in colors. Otherwise, the same colors of light of this, this H2 region are going to be blended with the bluish light of a neighboring part of the galaxy. And when that's all squished down at a smaller image scale, the color is not as distinct. It just looks blue. He just wanted his H2 regions. And I'm like, your picture is great. It's just the image scale is what's really harming the ability to see what you see in an image like this through a larger telescope. So that's another element of color contrast in images. There's color resolution, but there's also the dominance of the sky brightness itself.
All right, thank you.
Yeah, that wasn't really much. I didn't really tell you what to do. It really depends on the data. So if you presented me with an image, I might say some very particular things. But those generalizations that I just said, those are probably the important ones that usually are at play.
All right.
Adam, I have another question on that topic. For deep colors, do you, some people are just not even shooting luminance anymore. Like they're just spending all their time shooting the 3 color channels.
Right.
You find a benefit to that and just creating a pseudo luminance from that? And do you, what are the pros and cons?
Yeah. So, God, this comes up all the time. The idea behind creating a luminance image that, and when I say luminance, let me be very clear, literally clear. To create an image where you're using a clear filter has benefit only in certain situations to save time. You can always get an equivalent image just doing straight RGB. You may not be able to do it in the same amount of time. The benefit with doing a separate luminance is that you can bin the color, and that's where the time saving is for some sensors in some conditions. And the condition is that if you're looking at an object that's very dim, like a galaxy or a nebula, and it has very faint structures, if you're looking at a planetary nebula, there is no reason, or a globular cluster, there is no reason to bin the color data to actually acquire a separate luminance, because the signal that you're interested in is so bright that there's no time savings involved. The time savings that comes by binning the color, and that's why you would create a separate luminance. It just allows you to bin the color. Generally, binning the color is not a loss of spatial information because of the way that we perceive color images. You can get a slightly lower resolution color, apply it to a higher resolution luminance image, and everything looks great. The binning you can take advantage of because you're reducing effectively the read noise. You have the same read noise even though you now have a larger pixel that gives you a slightly better signal to noise ratio. It makes the chip or sensor act as if it is more sensitive than it otherwise was when you were just doing no binning, binned 1-to-1. So that is not true for all sensors. That's number one. Not all sensors have that characteristic that you get to take advantage of, that read noise characteristic. Most sensors, that's true. Certainly for CCD cameras, most sensors, that's true. Not all of them. With CMOS in particular, that's definitely not always true. There are CMOS chips that do not do binning well. And then there are certainly all of the one-shot color cameras, but you can't do any binning at all. So these are all the caveats to consider. But back to the big generalization is, if you're taking a picture of an object that's very, very bright, the Orion Nebula, the Andromeda Galaxy, the Ring Nebula, the Eskimo Nebula, M13, I don't know, name a bunch of those things. There is no benefit to doing a separate luminance. Just do RGB and then create, as you said, if you want to operate on a luminance so that you can do a different path in processing, create that synthetic luminance from extracting that information from the RGB. But if you're trying to get a picture of IC 342 or the tidal stream of some faint thing, the loops that run around, let me show you an example, beautiful example. I just posted it recently on my AstroBin site. A really good example. I don't know how to do. I'm new to this whole AstroBin thing. This is an excellent example. This is an object that has. Oh, I didn't do that right. Sorry. See, I told you I'm new at this. I think I just click on the image, right? Yeah. There's a full resolution. Here it is. I don't want to zoom out. I just want. There we go. So there's a set of galaxies here, and there's another one down at the, I can't get them both on the screen, but do you see how there's some faint stuff going on here, right?
Yeah.
And although this galaxy is really bright, but there are other faint elements that are not bright. Notice, for example, that this thing has these loops and this kind of tidal tail weird things going on. I would always go for doing binned color here. The color isn't really critical because these galaxies don't have a lot of small color detail. And I get the benefit of taking advantage of, in my case, that read noise advantage of the better the signal to noise value because I was using a CCD camera. And it saved me time, especially in my very particular case where I might be working with other individuals who can't do this for days on nights on end. So I needed to get as much data as I possibly could in a given amount of time to get the very best possible image, and binning then really did make sense. It was a time savings thing, and this is a good example of that. There are many other examples, I guess, but that's a good example. Another good example, I guess, if I go here, just one more good example, something like here, this is a good example. This dust cloud. This is a crazy, crazy dust cloud in Taurus. And again, it's not bright at all. It's basically black if you don't really do a long exposure. And the color variation is very small. It's mostly kind of brown. It has a couple little, variations here. So binning the color, no problem here at all. And I benefit from that effect of that read noise, signal to noise increase that I would get in this case. But that's just not always true. And I just want to make sure you don't walk away from this thinking, Adam said I should do it because there's a benefit. It's not always true, but it can be true in certain situations.
So Adam, was this a CCD chip
Yes.
that took this? Okay.
Yes. Yeah. Yeah. This was with collaborated with a friend. Some of you may know him. He has a very nice 24-inch telescope. And we spent a fairly, 13 hours of time on it. So we did a significant bit of time on this, but it's just a straight LRGB type image. Okay. So the other thing that I wanted to show, let's see my list here, is I wanted to highlight a couple of the things about pixel math, because that was something else that was suggested on the list. So if you're up for another 20 minutes or half an hour's worth of information, I can highlight a few things with pixel math. and then I will say that I've covered most of what was on the list. Would you be interested in a little bit more?
Absolutely.
Keep going.
Keep going. Okay, I'll do a little more. So, oh, that's my email. Let's see here. So this one, what I'm going to show isn't so much, I'm not going to be operating on an image like, you know, I can have any image really, but instead I'm going to literally be working with pixel math to demonstrate how useful it is. I do have an example though that I want to get to. And it does again deal with that object, that galaxy that I just took a picture of. But first, let me show you this. Let's see, I guess I can even do, now I'll just keep it like this. I'm not going to make it full screen. So the way pixel math works is, let me bring it up, I guess. It was here. Let's get rid of this. Let's get rid of this. We'll get rid of, here it is. And by the way, this might look a little different. The pixel math has changed. I mean, it still works in the same way, but there are some cool benefits now, improvements of this tool. So the way that this tool works is that you get to put expressions in here with our little mathematical equations or operations, I should say. And the way that an image is processed, and this is true in general, but it's the way in which we interact with an image, is that when we're looking at an image, these images are comprised of individual pixels, so you can see them right there. And if I go to the very top left, up here, this is the very first, well, I get, it might be up there in the black, but anyway, let's pretend this is the very first pixel in the image, right? And that pixel is where you begin to do whatever you're going to do, analyze the image, perform some mathematical operation. So pixel math then is you visit pixel number 1, you do whatever you commanded it to do here, then you visit pixel number 2, you do whatever it is you command here, you visit pixel number 3, you do whatever you command, and it goes across the entire first row in values of x. So in generally the standard here is that you have x in the horizontal direction and y values are in the vertical direction. That's normal. But what you generally do for images in the amateur world is you put the origin at the top left. So this pixel here is 0, 0. In fact, if I click here, you'll see that the x and the y value read, well, it says 3 because the actual 0, 0 is up here. But pretend this is 0, 0. So this is the top left of the image and the origin is at the top left corner. So you go across the image in one row and then you go to the next one down and you do another row. So you're varying x the first time and then you increase in y and then you go in all the x's again and then you increase in y and you go through all the x's again and so on. So you raster across the image doing whatever expression it is you put here. So I am now going to put an expression. It'll be the most boring expression you can put, but I put the number 1 here. So what's going to happen with pixel math is that if I apply this to the image, it's going to visit the first pixel and it'll put the value 1 here. Then it'll visit the second pixel and it'll put the value 1 here, and so on. So this is going to make a white picture when I apply here. And if you didn't know, and I'm assuming that everyone knows this, but in PixInsight, values of images are normalized between 0 and 1. That's actually very important to understand when you're now operating on pixels as we're doing here, to understand the values and the positions of things. So whenever we're talking about a pixel has attributes which includes its value and the position at which it's located in the array. But whenever we put an expression here, you just want to keep in your mind's eye that we're just talking about one pixel at a time. So sometimes these expressions look complicated, but we're only operating on one single pixel as we go through the whole image. There are some operations that take into account all of the pixels, like if I wanted to know what the median value is of the entire image, there's a function for that. But then I take that value and I do something to one pixel. So there are a number of functions that you'll find in pixel math, and I think I'd like to show you where they are here. If we go to, let's see, I just clicked on the bottom button. It's called the expression editor. It allows you to type in these expressions in the same way that I'm about to in that same place. But now I can look at all of the functions that this tool understands. And basically anything, any mathematical function that you would normally program with, it's all included in here. So a good one, for example, is, let's see, there's, well, I'm thinking what would be a good thing. I'm about to show you a good thing. Let's see, pixel random. Random's kind of fun. So random would actually just put a random value between 0 and 1 every time you visit a pixel. So you get a random looking image. It's not very exciting, but it would work. And there are many other values here as well. Many other functions, I should say, here as well. One of the functions that I want to point out is one that's a lowercase x. Let's see, did you put it in here that way? You should have. Yeah, here it is. The lowercase x with a little parentheses, that means it's a function, is the current horizontal position. So that's the position of the pixel, and the lowercase y is the position of the current pixel in the y direction. How that is important is in the following way. I'm going to do a little surgery here. Now this is just a random image here, right? This pixel is a, well here, let's do this one. Would you agree with me that this says y equals, let's see, the y here starts at what? 3, oh, so this is the y equals 3. So we had 1, 2, 3. This is the third y. And this x value here is what? Is it also, I hope, 3? Is that, or is it 2? Let's see, it's got to, yeah, it's going to be 2 because 0, 1, 2. So this value here, this thing here, it has an x value of 2. Do you agree with me? Because it goes here, I'm so zoomed in, it looks like it's decimals, but it's only a single pixel. If I wanted to, I could do something pretty cool. Let's see, if I, do I need to show you something else? Yes, I need to show you one other cool thing. There is an expression called if, and it is literally an if statement. Let me show it to you. Got ahead of myself. If is this thing. What you do is you put 3 things in parentheses. You put a condition, you put the thing that you want to have happen, or you put the other thing that if it didn't happen, the other thing that can happen. So there are 3 things that you put in here, and that's what I want to demonstrate. So I'm going to say if the position of where we're located at, that's that function, if it equals the number 2, then do something. I'm going to make it white. Otherwise, make it black. So this whole thing is going to basically, every time the x position equals 2, it should make a white pixel. Otherwise, every pixel will be turned black in this image if I apply this. So watch what happens. Watch this column right here. Ready? I made a mistake. I made a mistake because I always get that wrong. It's 2 I's and 1 F, not 2 F's and 1 F.
You got 2, you have 2 equal signs.
Oh, that's a good point. That's the Boolean. So if you type this thing, x equals 4, x equals 4, that's like a variable where you're saying the value of x is 4. X is 4. If you have 2 equals, this is a evaluation statement. This says, it's like asking a question. If x has the value of 4, but it's always in a question form because the answer is going to either be true or false. So when you have a double equals, it's a Boolean which is asking the question, is it true or false? X equals 4 can only be true or false. And that's exactly what we need here. We need, if the position, is it true that it's 2? If it is true, color the pixel a value of 1. If it's not true, color it to be 0. So that's the Boolean version of a conditional question, if you will. I got it right this time. Great. So do you see how it, and if I zoom out, you'll see just one strip going all the way down the image. It's just that I'm zoomed in so much. It's one tiny, tiny 1 pixel row on the very left edge of this image. So if I zoom all the way out, you won't see it because it's just a single pixel column. I said row, I should say column, going all the way down the image. Now I'm going to back up and show you one other way to do basically the same thing, which is that what happens if I do this crazy thing? So there is a construct, which is that thing, it says $T, that means the target image. You saw me earlier specifying names of images. So if I type the word image here, then what I could do is put the word image here. And what this means is that if X position equals 2, make it 1. Otherwise, leave whatever value the current pixel actually has. So image means take the value that you're currently at in the named image. So when I actually write the word here, it is indicating one of these things. It could be this image here, it could be this one, whichever name I put here, I would have to put gum15_RGB_R here if I wanted to refer to this one. This one I actually gave a nice name. Here, let me call it VVV for something really different. So if I wanted it to specify this thing, I would put VVV. But there's an easier way to do it, because in general, what I want to do is say, I want to apply to this image, so I can just drag my little triangle to the image I wanted to apply to. So instead of specifying a particular concrete name, you can use this token, this placeholder, which is $T. And what that means is that this means you're going to be using the caret, and wherever you put it, that name gets substituted here into the expression. So if I put the cursor here, what goes into target T, that little T thing, will be VVV. If I instead put it down here, what'll go in will be the name of this particular image will go into there. So that little $T allows you to use the caret and drag it to a particular image, and that name of that image, meaning this is the thing we're operating on, gets substituted into here. What will happen then when I do it this time is instead of it'll make still a white column, but it's going to leave all the other pixels alone, because what we're saying is if the value of the position if the position equals 2, change it to white. If it's not equal to 2, then change it to the value that was already there, which is don't change anything, because that's what this target T means. So we should just get a white column, and then none of the other values have changed. So that's an important idea to using pixel math, is you can now control elements of an image and interact with an image in a way that will allow you to specify particular pixels or do other kinds of operations. So for example, you can get very, very complex here. Remember how I did halos minus loom? I could put that, if halos minus loom equals, I don't know, whatever, 0.3, then do something or do something else. So you can get really complicated kind of expressions in here to do things, even in a single line. And then, of course, in pixel math, you can do many expressions that might help you perform some operation on these pixels as you raster across the image. Let me just show you another Boolean thing just because it's fun. What if I did the following thing? If I wanted to, instead of operate on let's light up a row rather than a column. So all I should have to do is just say if the Y position equals, I don't know what position I'm at here. Let's see, this Y is what? This is a Y of 30. So if I put 30 here, I should get a nice little plus sign. Yay, something like that. What if I only wanted to light up this pixel right here? Just the one pixel, right? So one more of these operations and I'll move on to something much more fun. But this pixel right here has an X value of 4 and a Y value of 32. So how would I do that? Well, what I could do is say if X position equals, what did I say, 4? And then there's a cool little Boolean thing, and that's the and operator. And I need a double, and the Y position equals, what, 32 I said? That should just light up one little pixel, like that. All right, so that gives you lots of control, but this might not, this exercise that I'm doing right now may not seem all that powerful, but if you go through it and you learn step by step, you know, you light up little pixels or you do these kinds of exercises, if you will, you'll very quickly be able to do some really powerful things. And I'd like to demonstrate that. So let me demonstrate one actual real powerful thing. Let me zoom out. I believe that you now understand that if I did the following, what happens if I just do this? If I say X position, what in the world am I going to get here for an answer? Does that make sense?
Any X?
Well, what's going to happen is this thing means, what is the X position at the very top left? It's 0, right? And what's
That's the default. Okay.
What's that?
You're going to get a gradient.
That's the.
Well, no, hold on. You're going.
Your reference right there is.
But you haven't got there yet. There's a step. So what is the X position of the top left pixel? 0, right? What's the X position of the next one to the right? It's a value of 1. Do you agree with that? X equals 1. That's the position. And then what's the value of X, the next one to the right? Of that is a value of 2. So if I do this, what I'm going to get is one black column and everything else should be white, because everything bigger than 1 is basically just going to be 1. Would you agree with that? If I zoom in more, you can see the one black column here, and then all the other values are going to be white. But you were heading in the direction that I wanted to go. Because really what I want is a gradient. And to make a gradient then, what I want is the first value over here, in the gradient, I want it to be 0. And I want the last value in the gradient on the right to be the value of 1. So what do I know about this image? I know how big it is. If we look here at the bottom, what is my size? This image is 3056 in size, in number of pixels across. So if I want this thing over here to be 0, the first value, then all I should have to do, well, let me do at the other end, because I think it'll make more sense. If I want the last value in my gradient to be 1, what do I need to do to the X position to make this value over here on the right be equal to 1? The X value over here is going to be 3056. So what do I need to do to it to make it equal to 1? I have an X value over here of 3056. So what do I need to do to the number of 3056 to make it equal to 1? What do I do to any number to make it equal to 1?
Set it equal to it, but we're trying to figure out how to make that X reference to your 3000 value.
Divide by the width.
So you divide by
that number.
So you divide by the number itself. Let me just zoom in here. So what I'm saying is, on the right side of my image, these X values here are all 3,555, whatever,
Right.
because it starts at 0.
Right.
So 3,030.55, right? These are the X values over here. And I want these values in my resulting image to be equal to 1. I want this value right here to be a little bit less than 1. And this value right here, a little bit less, going all the way to the left, all the way back to 0. So to make this value equal to 1, I divide by that number, the width of the image, 3056. Because I need 3056 to, that's what it'll be when it gets over here to the right, divided by 3056 will be equal to 1. So if I zoom back out, and we now actually do this, this should give us the gradient. Yay. But this thing that we just did is actually a function itself, which is just kind of cool. I had to know, in order to do what I just did, I had to know the width of the image. But what if we normalize the width of an image between 0 and 1? Then I never need to know the width of the image itself. So there's a function here that normalizes the size of your image to between value, like a fraction between 0 and 1. So halfway across your image is 0.5. Whatever number of pixels it is, it's 0.5 is the middle of your image. So the capital X with these little parentheses, these are the cool things you get to learn. That capital X does exactly the same thing. I'm going to undo what I did, and then I do this little cool thing here, and I get the gradient again. So that's just the normalized width, and I can do it if I wanted the gradient to be in the vertical direction. Of course, I would put the Y, and I can make a vertical gradient like that, so on.
Okay.
So
Sorry, I was thinking in classic programming terms. So sometimes object-oriented programming is not my first inclination.
So, from what I've just shown you, I've actually shown you what is necessary to create something really, really cool. And this is where I was heading towards. Let me show you my, my PowerPoint thing here. I just showed you how to consider the fact that when you use pixel math, you're rastering across the image, you can change the values of the image. You know that target T is a way to point at any image you want. So wherever you have a target T, it inserts the name of the image that you just dragged to into that spot. You saw me demonstrate, making a column and a row and making a single pixel and all that kind of stuff. I just demonstrated how to make a gradient. And from that, from what I just showed, you can do a number of really cool things now. I'm not gonna, this one is really easy. You can insert one image into another, which is the same thing as one of the processes in PixInsight, which is called substitute by preview. But you can do it on your own. And that's actually kind of nice to be able to do it on your own with your own expression. Another cool thing is I can share this expression with you, and then you have the same power. So if someone ever makes an expression, they can share these things, and then you instantly have the power to do whatever that expression was doing. So this is a cool expression that allows me to insert things into images. But the expression I really want to show you, let me just show you why that's powerful. So why that's powerful is this example here. Let me, current slide. One of the tools of PixInsight is a process called HDRMT. And HDRMT compresses the dynamic range and allows you to see both the faint and the bright things. So in this galaxy, if I just tried in some linear way, even most nonlinear ways, it's really tough to be able to see what's going on inside the galaxy. But HDRMT will result in an image that looks like here at the very bottom, which is cool, because then you see the inner part of the galaxy and the outer part of the galaxy. But HDRMT, the algorithm itself, it works in a way that it depends on the size, the number of brightnesses that are contained in the region that you're looking at. So if I applied HDRMT to the entire image, I would get a different answer than if I applied it to just a region right around the galaxy. So it's nice to be, and generally the result that you want is the one where you're honed in on the object. So it's nice to be able to create that preview. So I make a little tiny version of the image, I do my HDRMT, and then I write it right back into the same spot. And that expression that I just showed you is what allows me to do that. I can write it in right back to, all I need to do is tell it the coordinates of the preview. That's cool. I mean, that's just kind of fun to do. But the one that I'm really proud of is this one. So most astronomical objects, you know, they have some fairly simple attributes, their brightnesses, but also their shapes. And most things in astronomy, I mean, they don't really have very rectilinear forms. They're fairly smooth, curves, round, elliptical, I think is probably the most general way to characterize a lot of things in astronomy. And back in, whatever I said here, 2017, PixInsight did not have a way to basically easily create an elliptical mask of any sort. You could create a circular mask, but not an elliptical one. And I'm like, man, that doesn't seem right. And I had just gotten to the point of explaining things, understanding enough pixel math in the way that I just did with you, that I came up with, I want to do that. I think I should, I now know enough, I should be able to do that. So the first thing I had to do was look up the equation of an ellipse. You can find that on Google in a book. This is the very standard form of the equation. It has a lot of stuff in it because you have to specify for an ellipse where it is in X, Y in translation. You need to specify the rotation of the ellipse. So where it is in translation is the that X minus H thing. So the H and the K specify where in the image it is. The A value is the position angle, the rotation of the ellipse. And then you have these terms of A and B, which are the major axes and minor axes of the ellipse. That's what you need to do to specify the ellipse in this equation. And in this form of the equation, is this showing up on your screen? I can't see it, because on my screen it's hidden. There. You set this thing equal to 1. When this whole thing equals 1, you are specifying the boundary of an ellipse in this form. And so with this equation, I said, okay, I now have all I need. I can create, I can just tell it the position of the ellipse, where I want it to be in the image. That's no problem. I'm going to tell it the size of the ellipse and the A and the B values for the, you know, how stretched the ellipse is. That's no problem. I can specify the angle. So in pixel math, you can just put these things that you need to save in variables, set them equal to something. And then I have this crazy equation here, right? So I had to make my ellipse equation. So that equation calculates a value. And then I have my final little if statement there at the bottom. And that if statement, you now know enough to understand what I did. So let me explain what I did. The way an ellipse works with this equation is that if you put in a bunch of numbers here, and those numbers equal 1, you are on the boundary of the ellipse. If that number, let's say you put in an A and a B value and an X and a H and a whatever value, an A value, and the value is less than 1 in this equation, it means you're inside the boundary. You're actually inside the ellipse. And if the number is bigger than 1, then you're outside of the ellipse. So I have an if statement here at the bottom that says, if the calculated value based on the position of where we are in the array, if it is less than 1, we're in the ellipse. So if you're less than 1, then you do something. If you're not less than 1, then you just make it black. Now what I did, I'm going to say, is the clever part. Remember a moment ago how I described how you can make a gradient by taking the normalized width or dimension of the object and starting with a value of, say, 0 and going to the other value all the way to 1? Well, what I did here is I said, oh, so the value that I'm going to put into my, now that I know if I'm in the ellipse or not, the value I'm going to put in there is going to be either 0 near maybe the edge of the ellipse, going all the way to 1 when it's at the center of the ellipse. So all I do here is I take the ratio of those numbers, depending upon how far away I am from the center or the boundary of the ellipse, is going to tell me where I am in that normalized space. That actually tells me what value I need to put there, is that ratio. So that's what this little ratio here is just telling me. If I'm halfway in, this ratio here is going to equal 0.5. And so I'm going to get a gray value halfway between the edge of the ellipse and the center of the ellipse. What this does is this creates not only an elliptical shape, but a gradient within that elliptical shape. It creates an elliptical gradient mask, which I think is really cool. So let me show it to you. The expression is here. Let's see. I'm looking. Oh, I don't have my, I closed everything. Okay, hang on. I will open recent project this. Yes. So let's just open an image. It doesn't matter what. There we go. So there's an image, and I have pixel math probably here somewhere. Here it is. So I have a black image here, just so we don't have to look at the actual picture. And then I have that expression, which is my elliptical mask right here. So I put it in here, and just so you can see, in this new version here, let me make this look more neat. This expression, I will tell you, I cannot tell you how hard it was to get all of these parentheses correct. It's much easier to write that expression down than it is to get this right. I'm trying to find the end here. I think that's the end. Oh, that is the end. Okay. So I have the whole expression there, and I have my little variables here where I've assigned them the position in the image where I want my ellipse. So I want my ellipse to be centered on 1000, 1000. I want the A to be 200. I want the B to be 100. So this ellipse is going to be twice as long as it is wide. And I want the angle to be, I don't know, let's do a nice angle. Let's do 45. So it'll be rotated 45 degrees. That's it. I should now be able to put this here. And see, it makes an ellipse, an elliptical thing, right in my image. Isn't that cool? This should be at 1000, 1000 here, which it is. X equals 1000, Y equals 1000. So just to give you a sense, where is that if statement? Here it is, goodness. If I wanted to, instead of saying, you know, this equation here, instead of making a gradient, I could just say, if we're inside the ellipse, make it 1. If we're outside the ellipse, make it 0. I could do that. And that's just going to make a white, no gradient ellipse. But that works as well. And then one more kind of fun thing, which is, let's do, well, here, let me show you something else. If I were to change this to 135, then I'll have two crossed ellipses, which is just kind of cool. But in order for me to do that, you now know the trick. I can't have this be 0, because now if I kept this 0, I'll just get a new ellipse with everything else being black. But if I wanted a second ellipse on here, I need to make this target T so it doesn't change the other pixels. That should give me a crossed set of ellipses. Yeah. That's what I wanted to show you. But the cool part of this was actually, I think, the gradient, because to make a shape and then have a gradient, either you can apply it or not apply it, is a really cool thing to be able to do. So from this thing that I made, a cool tool was developed. Have any of you seen the game script? I don't know.
I was just going to ask you, the game script probably makes this a lot easier.
Well, yeah, because it does make it easier, because when I made the equation, I went on the forum and I said, look, I think this would be a cool tool. Here's the expression. Can someone make a script which does it? And Hermit Bornemann did that because of the expression that I made. Now, he added a lot of functionality, of course, that's just really remarkable. So let me go back to a point here where I actually have a real image instead of looking at my fake image. So here's the real image. And if you wanted to then with the game script. So all I'm doing, I was basically telling you the genesis of where this came from. And where it came from was my initial exercise in learning how to use pixel math. Everything I showed you was all that was necessary to make a new tool in PixInsight. So that, I thought that's pretty cool. So you can add a thing here, and all you're doing when you add this is you're specifying the X and the Y, the A and the B, should look pretty familiar, the position angle here, so this will just change that position angle, right? And then you can turn on or off the gradient mask, which is all that's doing in that equation, right, is turning off either that ratio part, and then you can make it a solid mask if you binary mask if you want, that just is going to put in a 1, or you can do the cool gradient mask part, so on and so forth. So that's how this tool was functioning, and it's really powerful. He also added the capability now that you can draw polygons and other things, which makes it a mask generating tool that's super, super powerful. But at the time that didn't exist, my little expression really helped me out. A really good example of that is, let me just show you one example. I'm not going to remember the number though. Let me think about that. So gallery / galaxies, close, right here. And then this one. When I was processing this image in particular, this is when I developed that elliptical thing, because I'm like, man, I really want to use HDRMT or whatever it is on these two galaxies and nowhere else, right? So I needed to make two elliptical things, and I couldn't, how am I going to do this? I couldn't figure out a nice way to do it. I mean, there are some ways that are kind of, you can try to use MMT and MLT to capture these kinds of structures, but you end up capturing a lot of other stuff that you don't really want to or have any need to. And so it was really powerful to be able to, at the time, make those two ellipses to allow me to process on these two galaxies without affecting anything else in the field. And I think it was to good benefit. Notice here that in this galaxy, because of HDRMT, you can almost see there must be another galaxy colliding with it, another small circular one that's lit up. You can see it's, I think these are two separate galaxies. And you can see the little star forming regions and H2 regions in this probably a dwarf galaxy being lit up due to the interaction with a much larger one. I think that's cool. Okay.
It is neat.
So the whole point of that exercise of trying to give you a little bit, and I'm happy to answer any questions about pixel math, but I wanted to step through those particular elements because I wanted to basically show you that even with a small understanding of a number of those features of pixel math, you really can create some innovative things that potentially don't exist, that no one has done. And that's really cool. Yeah. So that's 2 hours. So I'll pause now and see, are there any questions about anything?
Yeah.
And let me come back to the script because I can't even see you guys, so I don't know where you are. Hang on, where is everybody? I'm going to stop share. I'll share in a minute. Oh, there everyone is. Okay. Hi. Go ahead. What? Ask
Adam, on that elliptical with the superimposed dwarf, have you reported that? Have you gotten any interest in, is that new or?
I don't think it's known. At the time that I made the picture, you know, I released the image and I put the caption. Yeah, I didn't find any papers which highlight it. I think it's pretty cool.
Yeah, so it kind of went like professional astronomers after going, meh, we got bigger things.
No, I just don't think anyone, you know, there are lots of cool things in the universe. I just don't know that it's reached anyone's kind of radar.
So do you think
there probably is an astronomer out there that would be very interested. I just don't know who it is.
Because what comes to mind is it interacting or is the distance between the two, you know, you can't really tell when they're line of sight.
You would certainly want to do some kind of spectral, you know, spectroscopy to determine redshift and see if they are at the same distance and all that stuff. Yeah. But to my eye, it looks similar based on the, what I'm resolving in the one galaxy and I'm resolving in the other thing. And you could see a little bit of reddening through the little galaxy. So to me, it looks reasonable to think that they're near one another. It's not always true though, right? Stefan's quintet is a good example where one galaxy is very much in the foreground, then you got the other.
Yeah, an optical binary as opposed to a gravitational binary. So,
Right.
thank you, man.
Any other questions? Did that hit on the right notes as far as the things that were suggested?
It was excellent, Adam. Thank you.
Okay.
We're all stunned, man. We're all stunned.
Done.
That's right.
Well, the wave function collapsed then.
I know that pixel math is one of the most powerful features of PixInsight. I just had no idea you could do all what you just showed.
Yeah, and it is such a large subject because it really is the way to interact with an image. It's the way that all the processes interact with images that it's hard to, in a single session, really give a really good overview, because I tried to indicate why it might be powerful or useful, but there are a lot of things that I didn't say that are equally important. So consider what I showed only a very small aspect of its totality.
Yeah, I mean, I use it a lot just whenever I'm doing narrowband imaging to come up with like an SHO image, rather than just doing a simple combine of those layers. Part of those channels, I would just take like a formula for each one.
Yeah. But in that sense, one of the things that you're doing is, I mean, you have an entire image. So you're corresponding basically every pixel in one image with that same pixel in the other image.
Exactly.
Basically interacting between those two pixels as you go along. Which is, I mean, that's the other, I didn't demonstrate that, but that's obviously another way. Well, I did show when I was actually using pixel math. But that's another way that pixel math is very powerful. Yeah.
Right.
Yep.
By
But
the way,
cool.
do you know Casey Good?
I think we've corresponded before, and yeah, I mean, he actually helps out locally here, I thought, for a while. But I don't believe I've met him. I know he knows me.
Yeah, I took an intermediate astrophotography course that he was teaching up at Kit Peak last October.
Right. Okay. Kit Peak. That's where. Yes.
Yeah.
Sure. Yep. Yep.
Yeah.
Okay.
Good.
Real quick. So I'm going to mangle your words earlier, but close to the beginning, you mentioned that you were using a version that had some unreleased features.
Yeah. This is the new release. It's just being kind of bug checked by people. I actually haven't done much helping. But
so it's more an alpha or beta release then, or is it full release?
This will be, assuming that he fixes all the bugs that people find, I think that this is going to be the thing he releases.
Okay.
So it's an update.
Which was the follow-on question? When do you think that'll happen?
That I don't know, but my sense from Juan, based on the amount of feedback he's getting, is that this would be something relatively soon. I would guess less than a month, weeks. I mean, I can't imagine it being more than a week or two, but I really don't know, how it works. Because this is.
Do you have a second career as a lawyer?
No,
sorry.
I just don't know, man.
I know. The way you that's right.
The reason why, let me tell you, the reason why I don't know is that this is he just recently, Juan, that is, who's the author of PixInsight, he knighted me, basically. He put me on the PixInsight team, which just means that I'm now in the group of people who he'll send a release to have a look at. Basically, that's all that means. But this is the first time for me, so that's why I don't know how it works. I don't.
Sure.
Adam, I just had two real quick questions. Earlier, you mentioned your website. I've been a fundamentals customer for a while. I really love your.
Excellent. Thank you.
sort of piggybacking on that, would you give just a really quick, like, what is the difference between the fundamentals and the horizons?
Sure. Wow.
And then piggybacking on that, I know a lot of us use the CMOS cameras.
Yeah.
And you mentioned something about the differences, and I was just curious if you were doing any material that sort of highlights the differences in the hardware side.
There, yeah, you know, okay, so let's see, where do I want to start? Let me do that one first. The CMOS stuff, one of the areas that I've really been trying, because I'm using it to try to get people to, you know, see my other stuff. But on my, I don't know where it is now. Okay. On my YouTube site, I have a number of tutorials. So how do I, what's the best way to do this? If I do this? No. How about this? Oh, I like that. And then I have a playlist like, where do I find playlists? I have these are playlists. So one of the things that I'm doing is I'm highlighting various elements of CMOS vagaries, call them that, where, you know, CMOS chips and sensors are a little bit different than CCD chips in that same way. So there are things to look out for, and I'm trying to make some videos which highlight what some of those differences are. Another good set of tutorials that I have, again, online is there's a script in PixInsight that is what allows you to calibrate and potentially also register and combine the images. But it's a general purpose script that you need to understand how it works. And part of that understanding is linked to the sensor itself, because, for example, some CMOS sensors, you need to take very particular frames, which are unfortunately called flat darks. I would call them electronic signature frames, but you need to specify those to match exactly the flat field frames. If you don't, and you don't do it right, and you click on other things like optimize for dark frames and other things, you will get the wrong answer when you try to calibrate data, and it causes no end of confusion to people. So that's another area for CMOS users I would highly recommend. If you visit my YouTube videos, I have some CMOS specific things as well as the WBPP set of videos. As far as my site is concerned, let's see, if I do close this and do this, and, it gets in the way. There. I have two basic parts of my site. One is what I call fundamentals, and that does not mean, and I hope you as a customer would agree with me, it doesn't mean that it is beginners. That's not the way that I've structured this. Fundamental concepts, techniques, whatever they might be that I'm calling them, are things that I just think, complex or not, are necessary for people to understand in order to basically make their way around PixInsight and do astronomical image processing. In fact, many of the concepts that I try to explain are independent of the software itself. But as it relates to the software, I explain all of those concepts. So I think you can appreciate in what I did tonight. I tend to be verbose. I talk about a lot of things. That allows me to go really dive into a lot of the subject matter. And so fundamentals is that. You'll find that, you know, I have lots of videos, and if you look at the times on these videos, someone complained, let's see, I don't know where it is. I have a DBE here, right? Where's DBE? It's probably under, I don't know where it is. There, good. So DBE, I have 1, 2, 3, 4, 5, 6 sections, and that totals 2.5 hours of material on one process. DBE, that's it. That's all I talk about. So some people say, oh my God, I don't have time for that. You know, well, that's a different kind of way of approaching image processing. The way that I'm approaching this is I really do explain as much detail as I can, not only what the thing is, but why you might be doing it. I really do explain some of those things so that you can potentially, like I did with Pixel Math, you can make your own innovations. You can solve your own problems, not because someone actually had a recipe which shows you the answer, but because you understand the fundamental concept, you can do it yourself. That is why it requires this level of explanation. And I think it's a very powerful way to learn something like PixInsight and so on. So fundamentals is something that I almost always recommend people, if you're interested in my stuff, basically do that first. Horizons is different in the sense that I already make the assumption that you watched all of that stuff. And because I relate, I refer to it, I use that as my foundation for doing all these other things. And all this other stuff is really my opportunity to finally, whenever I come across a problem and I found a solution, I make a recording of that. And many other people have those problems. I can't manufacture those problems, those techniques, because I may not have encountered it. There is no recipe that will allow me to see that problem in advance. So Horizons really is a collection of all of the creativity of everything that I know and do in image processing, I put here. And one of the most fundamental ways that I put it here is I have these object-specific tutorials. So not only do I show in gory detail everything that I did to create the image, but I also make the data that I used available. And this data is about as good as it gets. Most of this data comes from, it comes from Chile, comes from the Mount Lemmon and a 32-inch telescope, though you might think, oh, well, I'll never have data like that. I also worked on someone's data that came from the middle of Detroit. So I've got data of all of all kinds and the techniques of all manner. I think certainly it's the very best that I can do to show fully everything that I know in astronomical image processing.
Hey, Adam,
Yeah.
I just wanted to let you know that I saw your name on this presentation. I thought, that sounds familiar.
Okay.
And you responded here recently to one of my posts on the PixInsight forum.
I hope I was nice.
Oh yeah, it was. It was about the WBPP.
Good.
And I was having all sorts of problems with it, and you just touched on it just tonight about the calibration frames. And I looked at your videos, and it cleared up things really well.
Good.
In fact, the picture in my background was the one I was working on at the time. So, yeah.
Oh, okay, good.
So thanks, and finally you got to meet you.
Very good. Excellent. Well, tonight I have to actually observe. I can maybe I should show you this here. I'm going to share again. If I can find the thing fast enough. So at my job, I work at the Department of Astronomy at Stewart Observatory, and I operate a telescope that allows us to do certain kinds of observations. One is for a night sky brightness. It also does some satellite work. Oh, he might be doing something, but hopefully I can get in here. So he's already opened up. So this is the astrograph. And it will be used tonight to do both satellite observations, most interestingly of the Starlink satellite observations. Oh, I'm gonna leave and let him do his thing here. Hold on. Okay. As well as I will be using it later to do a night sky brightness survey. So it's currently sitting at Biosphere. It's a mobile observatory that we bring around to different locations. It looks like tonight is going to be clear. So I should be getting ready to go set up my particular experiment here in just a moment.
What's the size of that telescope?
So that's the Epsilon 180 Takahashi. So it's basically a 7-inch telescope. Did I do that math right? I think so. Any other last things?
Thanks. This was very, very helpful.
Okay.
Thank you, Adam.
Thank you.
Well, thank you for hanging out. I know that was it's a lot of information, so I really appreciate you having the patience to let me go through it and show you all that stuff.
I appreciate your time tonight, Adam.
Thank you, Adam.
Okay.
Thank
Thank
you.
you.
All right. Have a good night.
You too.
Fun observing.
Thank you.